When dealing with multiple branch circuits entering a junction box, it's essential to understand the proper handling of grounded conductors, sometimes referred to as neutral conductors. The electrical code typically requires that each grounded conductor for a branch circuit must originate from the panel and extend to its designated point of use. In other words, you cannot combine the grounded conductors of multiple branch circuits into a single, larger conductor within a junction box and then run that single conductor back to the panel. There are several reasons for this requirement. Firstly, proper identification and isolation of each branch circuit's grounded conductor are necessary for troubleshooting and maintenance. If grounded conductors are combined, it becomes difficult to isolate individual circuits to identify faults or perform work safely. Secondly, combining grounded conductors can lead to overloading of the single conductor. While it might seem logical to size a single conductor based on the total anticipated current, this approach fails to account for potential imbalances in the load served by the individual branch circuits. If one circuit carries a significantly higher current than the others, the combined grounded conductor could become overloaded, leading to overheating and potential fire hazards. Thirdly, the electrical code addresses the specific sizing and installation requirements for grounded conductors. Combining grounded conductors from multiple circuits would violate these requirements and could create an unsafe installation. The National Electrical Code, or NEC, provides detailed guidelines for the proper sizing and installation of grounded conductors. These guidelines are designed to ensure that the grounded conductors can safely carry the anticipated current and provide a low impedance path for fault currents. In the scenario of 420 amp 120 volts linear load branch circuits, it might seem tempting to run a single 40 amp conductor back to the panel. This would, however, violate the electrical code and could create a dangerous situation. Each 20 amp circuit must have its own dedicated grounded conductor, sized appropriately for the circuit's ampacity, typically 12 American wire gauge copper for 20 amp circuits. These grounded conductors must originate from the panel's neutral bus and extend to the junction box, where they connect to the corresponding devices served by the branch circuit. Inside the junction box, each individual grounded conductor must be connected to its respective neutral terminal or conductor. You cannot simply splice all the grounded conductors together and run a single conductor back to the panel. This practice is prohibited because it compromises the integrity of the grounding system and can create a path for unwanted current flow. To clarify, for 420 amp 120 volt circuits, you would need 4 separate grounded conductors running from the panel to the junction box. Each of these conductors would be sized according to the requirements for a 20 amp circuit, typically 12 American wire gauge copper. These individual grounded conductors are then connected to the corresponding neutral terminals or conductors within the junction box, maintaining the separation and integrity of each branch circuit's grounding system. The concept of running a single, larger conductor instead of individual grounded conductors for each circuit may seem appealing from a cost or convenience perspective. However, the risks associated with this practice far outweigh any potential benefits. By adhering to the electrical code and maintaining separate grounded conductors for each branch circuit, you ensure a safe and reliable electrical system. Furthermore, it's important to differentiate between grounded conductors, which carry current under normal operating conditions, and equipment grounding conductors, which are intended to provide a path for fault current only. Equipment grounding conductors are typically bare or green insulated wires that connect the non-current carrying metal parts of electrical equipment to the grounding system. These conductors are designed to trip a circuit breaker or fuse in the event of a ground fault, preventing electric shock hazards. The electrical code permits the sharing of equipment grounding conductors in certain situations, but this is subject to specific requirements and limitations. In the case of multiple branch circuits running to a junction box, you may be able to share a single equipment grounding conductor, provided that it is sized appropriately for the largest overcurrent protection device protecting any of the circuits. However, it's crucial to consult the electrical code and follow the manufacturer's instructions to ensure that the equipment grounding conductor is properly sized and installed. The key takeaway is that grounded conductors must always be kept separate and distinct for each branch circuit, while equipment grounding conductors may be shared under certain circumstances, subject to the requirements of the electrical code. Always refer to the latest edition of the NEC and consult with a qualified electrician to ensure that your electrical installations comply with all applicable regulations and safety standards. Grounded conductors, as per the NEC, serve a vital role in maintaining electrical safety. They provide a return path for current, ensuring that electrical circuits function correctly. When a fault occurs, such as a short circuit, the grounded conductor, in conjunction with the equipment grounding conductor, facilitates the flow of fault current back to the source, causing the overcurrent protection device, such as the circuit breaker or fuse, to trip and energize the circuit. This rapid energization prevents dangerous voltage from being present on the metal parts of electrical equipment, protecting people from electric shock. Furthermore, grounded conductors help to minimize voltage fluctuations and maintain a stable voltage level throughout the electrical system. By providing a low impedance path for current flow, grounded conductors reduce the voltage drop between the source and the load, ensuring that electrical equipment receives the proper voltage for optimal performance. In addition to their safety and performance benefits, grounded conductors also play a role in reducing electrical noise and interference. By providing a stable reference point for voltage, grounded conductors help to filter out unwanted signals and minimize the effects of electromagnetic interference. This is particularly important in sensitive electronic equipment, where noise and interference can disrupt operation and cause malfunctions. The NEC specifies the requirements for grounding and bonding electrical systems to ensure electrical safety. Grounding refers to connecting the electrical system to the earth, while bonding refers to connecting the non-current carrying metal parts of electrical equipment together to create a low impedance path for fault current. Both grounding and bonding are essential for providing a safe and reliable electrical system. The NEC mandates that all electrical systems be grounded and bonded in accordance with its requirements. This includes grounding the service entrance, grounding the neutral conductor, and bonding all metal enclosures, raceways, and equipment. The specific requirements for grounding and bonding vary depending on the type of electrical system, the voltage level, and the application. It is crucial to consult the NEC and follow the manufacturer's instructions to ensure that your electrical installations comply with all applicable regulations and safety standards. When working with electrical systems, it is always important to take precautions to protect yourself from electric shock. This includes wearing appropriate personal protective equipment, such as insulated gloves and safety glasses, and using insulated tools. Before working on any electrical circuit, always energize the circuit by turning off the circuit breaker or removing the fuse. Verify that the circuit is de-energized by using a voltage tester. Never work on live electrical circuits unless you are qualified and authorized to do so. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician to do the work for you. Electricity can be dangerous, and it is important to take precautions to protect yourself and others from harm. In summary, the proper handling of grounded conductors and junction boxes is critical for electrical safety and compliance with the NEC. Grounded conductors must be kept separate and distinct for each branch circuit, while equipment grounding conductors may be shared under certain circumstances. Always refer to the latest edition of the NEC and consult with a qualified electrician to ensure that your electrical installations comply with all applicable regulations and safety standards. Never attempt to combine grounded conductors from multiple branch circuits into a single conductor within a junction box, as this practice violates the electrical code and can create a dangerous situation. Each circuit requires its own properly sized grounded conductor that runs directly from the panel to the point of use. Adhering to these guidelines ensures a safe and reliable electrical system. The 20-amp circuits each require a 12 American wire gauge copper wire for the grounded conductor, running directly back to the panel separately. The equipment grounding conductors can be shared, as long as they are sized appropriately for the largest overcurrent protection device. However, the separate grounded conductors are a must for safety and NEC compliance. Remember, proper grounding and bonding are essential elements of a safe electrical system. Consult the NEC for specific requirements related to your particular installation and always seek the expertise of a qualified electrician when in doubt. Ignoring these guidelines can lead to hazardous conditions and potentially life-threatening situations. Prioritizing safety and adhering to established electrical codes are paramount in all electrical work. The NEC Table 310.15b16 provides ampacity values for insulated conductors rated up to and including 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air and installed in raceways. This table helps determine the appropriate wire gauge for different ampacities considering the temperature rating of the conductor. For example, 12 American wire gauge copper wire, commonly used for 20 amp circuits, has a certain ampacity rating depending on its insulation type and temperature rating. If the 12 American wire gauge copper wire has a 75 degrees Celsius insulation rating, such as THHN, it can typically handle 20 amps safely. However, it's crucial to consult NEC Table 310.15b16 to verify the specific ampacity for the given conductor type and installation conditions. In addition to ampacity, voltage drop is another important factor to consider when sizing conductors. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause electrical equipment to malfunction or perform poorly. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, conductors should be sized large enough to carry the load current without excessive voltage loss. The length of the conductor also affects voltage drop, with longer conductors experiencing greater voltage drop than shorter conductors. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by circular mils, where K is the direct current constant, typically 12.9 ohm circular mils per foot for copper conductors, I is the current in amps, D is the one-way distance in feet, and circular mils is the cross-sectional area of the conductor in circular mils. This calculation helps determine the appropriate conductor size to maintain voltage drop within acceptable limits. The NEC also provides guidelines for dirting conductors when multiple conductors are bundled together in a raceway or cable. When conductors are bundled together, they generate heat, which can reduce their ampacity. The NEC requires that the ampacity of conductors be derated when the number of current-carrying conductors in a raceway or cable exceeds 3. The derating factors vary depending on the number of conductors and the ambient temperature. For example, if there are 4 to 6 current-carrying conductors in a raceway, the ampacity of each conductor must be derated to 80% of its original value. If there are 7 to 9 current-carrying conductors, the ampacity must be derated to 70%. These derating factors help ensure that the conductors do not overheat and cause a fire hazard. In addition to derating for the number of conductors, the NEC also requires that conductors be derated for ambient temperature. The ampacity of a conductor decreases as the ambient temperature increases. The NEC provides correction factors for different ambient temperatures. For example, if the ambient temperature is above 30 degrees Celsius, the ampacity of the conductor must be derated. The specific correction factors depend on the insulation type of the conductor. These correction factors help ensure that the conductors operate within their temperature limits and do not overheat. When selecting conductors for an electrical installation, it is important to consider all of these factors, including ampacity, voltage drop, derating for the number of conductors, and derating for ambient temperature. Consulting the NEC and following the manufacturer's instructions will help ensure that the conductors are properly sized and installed. In this specific scenario of 4 20 amp 120 volts linear load branch circuits going into a junction box, each circuit would require a 12 American wire gauge copper wire for the grounded conductor, running separately back to the panel. The equipment grounding conductor could potentially be shared, sized according to the requirements for the largest of a current protection device. Remember to consult the NEC for specific requirements and derating factors, and always prioritize safety when working with electrical systems. A linear load is an electrical load where the current is proportional to the voltage. Resistive loads, such as incandescent light bulbs and heaters, are examples of linear loads. Nonlinear loads, on the other hand, draw current in a non-sinusoidal manner. Examples of nonlinear loads include electronic devices with switching power supplies, such as computers, televisions, and LED lighting. Nonlinear loads can generate harmonic currents, which are currents with frequencies that are multiples of the fundamental frequency, typically 60 Hz. Harmonic currents can cause various problems in electrical systems, including overheating of conductors and transformers, voltage distortion, and interference with sensitive electronic equipment. To mitigate the effects of harmonic currents, it is important to use appropriate mitigation techniques, such as harmonic filters and reactors. The NEC provides guidelines for dealing with harmonic currents in electrical systems. These guidelines address the sizing of conductors and transformers, as well as the use of harmonic mitigation equipment. When dealing with nonlinear loads, it is important to consult the NEC and follow the manufacturer's instructions to ensure that the electrical system is properly designed and installed. In the case of the 420 amp 120 volts linear load branch circuits, the harmonic currents are not as significant of a concern compared to nonlinear loads. However, it is still important to ensure that the conductors are properly sized and that the electrical system is grounded and bonded in accordance with the NEC requirements. For the grounded conductors, remember that each 20 amp circuit needs its own 12 American wire gauge copper conductor running separately back to the panel. The equipment grounding conductor may be shared, as long as it is sized appropriately for the largest overcurrent protection device. Always prioritize safety and consult the NEC for specific requirements.